Then we will see input impedance of open and short circuited lines in transmission lines and RF system. So here the electrical lines which are used to transmit the electrical waves along them are called transmission lines. The primary constants are R, L, C, G, that is resistance, inductance, capacitance and conductance. The secondary constants are Z0, that is characteristic impedance, and gamma, propagation constant. So propagation constant consists of alpha and J beta. So alpha is attenuation factor, beta is phase constants, we already known that. So characteristic impedance is ratio between Z and Y, that is Z by Y, square root of Z by Y ohms, and propagation constant equal to square root of Z into Y. Here Z equal to R plus J omega L and Y equal to G plus J omega C. Here propagation constant equal to multiplication of Z and Y. Here in this circuit we will see here the load, that is ZR, in receiving impedance receiver side, the circuit is terminated with the ZR. Then the ES is the supplied voltage. Then the circuit consists of the so many T networks, that is cascade of T networks. So here Z is the impedance, Y is the admittance, that I and E are the point where the cascade section T starts. Here the length of the cascade section T section is ds. So the S is the point from the load. So here in the high frequency the resistance and conductance will be very small, so it will be almost 0. So the impedance and admittance conductance only. So impedance consists of J omega L and admittance Y consists of J omega C. So the characteristic impedance is Z0 in terms of R0. So the propagation constant consists of only beta value but not alpha value, because alpha equal to 0. So the general solution of transmission line, the voltage ES and current IS equations are ES equal to ER cos beta S plus J IR R0 sin beta S, IS equal to IR cos beta S plus J ER by R0 sin beta S. So here these two equations derived from general solution of transmission line when we are applying the J beta value. Okay, the length of the line S is terminated with ZR. So here the total input impedance Zin equal to ratio between ES and IS. So here ES is ER cos beta S plus J IR R0 sin beta S, and IS equal to IR cos beta S plus J ER by R0 sin beta S. So this is the radio. So that is the ratio. Here we have to solve the value. Here R0 down is there, so it will you multiply here and you total R0 will go up. So here R0, here IR R0 will come, here this R0 will go up, and again you divided full terms by IR. So ER by IR, here IR will get cancelled, here cancelled, here ER by IR. So here ER by IR we know that is ZR, then cos beta S plus J R0 sin beta S plus here IR we cancelled, so here cos beta S only, here J ER by IR, here it is ZR sin beta S. Then again if you divide cos theta by full terms, so here if you divide cos theta then it will be cancelled, that is cos beta S if you divide both sides. So here cos beta S if you divide, this term will get cancelled, so balance term ZR will be plus J and IR already cancelled, so R0 will be there. So sin beta S by cos beta S equal to tan beta S. Then down if you divide here, that is here if you already multiplied, R0 will be there, IR cancel. So here now we are dividing cos beta S means, so cos beta S will get cancelled, so balance R0 only will be there, plus J ZR will be there. So sin beta S by cos beta S will become tan beta S. So the final answer is Z input impedance Z in equal to R0 into ZR plus J R0 tan beta S by R0 plus J ZR tan beta S. So Z in is a complex value. So here we will see the effect of input circuits, that is input impedance of open circuit condition and short circuit condition. First we will see the open circuit condition. So what is the effect, that is what is the value of input impedance. So consider the input impedance in of the transmission line Z input equal to R0 equal to ZR plus J R0 sin beta S, that is tan beta S by r naught plus j zr tan beta s. So the line is open circuited at the receiving end, then zr becomes infinitive, right? So the input impedance is how? If you see the equation zr, if you divide all the terms by zr, then first term will become 1 plus j r naught by zr tan beta s. Here r naught by zr plus j tan beta s. So if you take zr equal to infinitive, then here 1 will be there, r naught by z naught equal to becomes 0. So this term won't be there. So first value 1. Okay, here r naught by zr value is there, then if you put zr equal to infinitive, this term will become 0. So balance term is j into tan beta s. So this is the value. Then 1 by j becomes, we are taking to upside, then it is minus j r naught, then 1 by tan beta s equal to cot beta s. So this is the formula, that is final solution, z input equal to minus j r naught cot beta s. This is the equation of open circuit condition. So we already know that beta equal to 2 pi by lambda. So ZOC, that is in impedance of open circuit lines, equal to minus j r naught cot beta s. So it is purely reactive elements, it is represented by x of s. So it is reactive means, that's why we are representing j x of s, which is equal to minus j r naught cot beta, we applied here 2 pi by lambda s. So here x of s, r naught goes this side, so x of s by r naught, j got cancelled, so minus cot 2 pi by lambda s. So here if you calculate the distance, that is variation of x of s ratio with the distance. So first if you put s equal to 0 in the equation, then cot 2 pi by lambda into 0, cot 0. So it is infinitive, the ratio value infinitive. S equal to lambda by 4, cot 2 pi by lambda into lambda by 4, cot pi by 2, then 0, that value. So ratio value xs by r naught equal to 0. S equal to lambda by 2, cot 2 pi by lambda into lambda by 2 will become cot pi, then it is value infinitive. So x of s r naught equal to infinitive. Again the distance s equal to 3 lambda by 4, then if you multiply here, then value, final value cot of 3 pi by 2, which is equal to 0, x of s by r naught equal to 0, then s equal to lambda, cot 2 pi by lambda into lambda, if you put, it cancel, so cot 2 pi, it is infinitive. So ratio also x of s by r naught equal to infinitive. Then if you take the graph of x of s with distance s, so if you initially it is 0, so at the terms of lambda by 4, lambda by 2, 3 lambda by 4 and lambda values, so if you put the x of s values, the graph is like this. So here lambda by 2 and 3 lambda by 4. Then for first quarter wavelength, the open circuit line act as a capacitance value. Then we will see the input impedance of short circuited line. So here again we will take the input impedance equation only. Z input equal to r naught zr plus j r naught tan beta s by r naught plus j zr tan beta s. So the line is short circuited, means at the receiving end, then zr equal to 0, we are removing zr, so we are short circuited. So zr equal to 0, the input impedance z0, if you put zr equal to 0 term plus first term will become 0, then j r naught tan beta s, here zr 0 means down term, only r naught will be there, so r naught cancel, then balance j r naught tan beta s. So this is the equation at a short circuited condition. If you put the beta value 2 pi by lambda, then z OC and ZSC will become purely reactive element, and let it be denoted as x of s only. Here j x of s equal to j r naught. So here that is z short circuited input impedance is j r naught tan beta s is purely reactive, then let it be denoted by x of s. So here j x of s equal to j r naught tan 2 pi by lambda s, then x of s by r naught equal to tan 2 pi by lambda into s. Okay, then zs j r naught tan beta s is purely reactive, let it be denoted by x of s. So j into x of s, so it is j r naught tan 2 pi by lambda s. So here this r naught goes down, here x of s by r naught equal to tan 2 pi by lambda s. So here if you see the x of s by r naught variation, that is with the distance s. So if you take the different values of s, 0, lambda by 4, lambda by 2 to 3 lambda by 4 lambda. So here if it is s equal to 0, then if you put tan 0 0, then ratio also 0. Here s equal to lambda by 4, then tan pi by 2, it is infinitive. So ratio x of s by r naught equal to infinitive. Here s equal to lambda by 2, here tan pi answer, then it is ratio 0, here also 0, then s equal to 3 lambda by 4, then tan 3 pi by 2, which is infinitive, ratio also infinitive. So s equal to lambda, then tan 2 pi equal to 0, ratio also 0. So here that is graph of to x of s by r naught with the distance s. So here you see compared to last graph, this lambda by 4, that graph will be started, here it is starting with 0. So here in the first quarter of the line started act as a inductance value with the distance. You see that you can compare the graph. This graph will started here lambda by 2, here lambda by 4, but previously the graph shown at lambda by 4 and 3 lambda by 4. Okay, so here the variation of input impedance are in open circuited line. So here the circuit, it is a open, here it is E and I ratio, here is the Z input impedance with the distance lambda by 4 and lambda by 2, 3 lambda by 4 and lambda. So the impedance values is here, so 0. Here current values is like this graph, that is voltage value, he will start from this value. Okay, so here the terminated end is open, the impedance is high. So line act as a parallel resonance circuit. The current is always 0 and voltage is maximum because it is open circuit. So here after every half wavelength distance, the condition of voltage and current will repeat themselves. Current will be repeat themselves. So here in this open circuited condition, so voltage maxima and current minima at the time, and the next time the voltage minima means the current maximum will occur. So after quarter wavelength lambda back, the input impedance is low resistance. So that time the line will act as a series resonance circuit. So between quarter wave and half wavelength, between quarter wave and half wavelength, can see the input impedance is inductive. Input impedance is inductive. So here next one will see the variation of input impedance in short circuited line. So here the short circuited line is in this. So here I and current value, so is here, so down, then it is starting from here, it is a full cycle. Here impedance Z value is like this. So you can compare previous diagram graph also, this one also. So here the line is short circuited, at terminating end the voltage is 0 and current is maximum. Voltage 0 but current is maximum. After every half wavelength distance, this condition will of voltage and current will repeat themselves. That means voltage maxima, current minima, and current maxima, voltage minima, like that. So after quarter wavelength back, the input impedance is high resistance. Here after length back, the input impedance is high resistance. So here the line acts as a parallel resonance circuit. So between quarter wave and half wavelength, the impedance, input impedance is capacitive. Okay, so in this input impedance for different wavelengths of open circuit and short circuited line, here if you see the different wavelength lambda by 6, it will act as a inductive. Here 3 lambda by 8, this act as a capacitive. Then Z input lambda by 2, it will act as a it is act as a small resistance. So inductance and capacitive combined, then it is a small resistance. Okay, shorted line, this is the different input impedance for different wavelength of short circuited line. Then again input impedance for different wavelength of open circuited line. Here open circuited with length same one is capacitive, but short circuited line it is a inductive, but open circuited line it is capacitive. Then here with length 3 lambda by 8, then here in open circuit line it is inductive, here it is capacitive, short circuited line. Okay, so here if you length lambda by 4, if it is in short circuited, it will say series connection of j omega, that is L and R, okay, C, L and C, it is equivalent to small resistance. Here in lambda by 2 in open circuited line, the capacitor and inductance is parallel circuit, so it is very high resistance. So these are the input impedance at open circuit and short circuit lines. Thank you.